So in this session we'll be looking at the AQA Combined Science Trilogy paper, Physics Paper 1 Higher Tier, and this is from the year 2019. It's always a good idea to download the paper from the description below, have a go yourself and then follow through with this video to see how you did. A student investigates how the current in a resistor varies with the potential difference across the resistor, and we have the diagram here. So we've got figure 1, the student connected an ammeter and a voltmeter in the circuit. What is the correct way to connect the ammeter and the voltmeter? So the ammeter should be in the circuit, so that's in series with the resistor, so it's going to be one of these two, and the voltmeter is always in parallel across the resistor, so that would be this one here. So the correct answer is here. The student increased the resistance of the variable resistor. How did increasing the resistance after the current, how did the increasing the resistance affect the current in the circuit? And if you increase the resistance, then the current is decreased. How should the student change the circuit to give a negative value for the current and potential difference? So here you'd have to reverse the connections to the cell. Name the type of relationship between the current and potential difference for a resistance at constant temperature. So the relationship would be as one increases, the other increases, so that is directly proportional. Write the equation which links current, potential difference and resistance. So that equation is V equals IR. So that's the potential difference equals the current times the resistance. The current in the resistor was 0.12 amps when the potential difference across the resistor was 3.0 volts. Calculate the resistance of the resistor. So if V equals IR, then from our information we have the current as being 0.12. We are calculating the resistance and we know that the voltage was 3.0 volts. So that means 3.0 divided by 0.12 would give us our resistance, and if we calculate that out, the resistance is 25 ohms. A scientist cooled the air inside a container. The temperature of the container changed from 20 degrees Celsius to 0 degrees Celsius. The volume of the container stayed the same. Explain how the motion of the air molecules caused the pressure in the container to change as the temperature decreased. So here, the pressure is going to decrease overall, and this is because the molecules will have less kinetic energy, and if they have less kinetic energy there's going to be fewer collisions with the wall of the container, making the pressure decrease. The air contained water that froze at 0 degrees Celsius. The change in internal energy of the water as it froze was 0.70 kilojoules. The specific latent heat of fusion of water is 330 kilojoules per kilogram. Calculate the mass of ice produced and use the physics equation sheet to help you. So if we look that up, we know that the energy is going to be the mass times the latent heat. So the energy we have is 0.7 kilojoules, and we will have our mass, which will be produced in kilograms, times our latent heat, which is in kilojoules per kilograms, so that is 330. So if we rearrange our equation here, we would get our mass being 0.7 divided by 330, which would give us a mass of 0.0021 kilograms. The air also contained oxygen, nitrogen and carbon dioxide. And if we look at oxygen, oxygen boils at minus 183 degrees Celsius and freezes at minus 218 degrees Celsius. Nitrogen boils at minus 195 degrees Celsius and freezes at minus 210 degrees Celsius. And carbon dioxide sublimates at minus 78 degrees Celsius, which means it changes straight from a solid to a gas. The scientists continue to cool the air to the temperature of minus 190 degrees Celsius. So for each one, we've got to say which state it would be at minus 190 degrees Celsius. So if we look at oxygen, oxygen has not reached the boiling point yet, so it's definitely not going to be a gas. However, the temperature is above the melting point, so that means oxygen at minus 190 degrees Celsius should be a liquid. Now, if we look at nitrogen, nitrogen boils at minus 195 degrees Celsius. So that means if we've got the temperature at minus 190 degrees Celsius, then the nitrogen would have boiled and would be a gas. And then lastly, we've got the carbon dioxide, which sublimates at minus 78 degrees Celsius. So it's not the temperature at which it has turned into a gas, which means it must still be a solid. Air is contained in a small amount of argon. As the temperature of the air decreases from 20 degrees to minus 190 degrees Celsius, the argon changes from a gas to a liquid to a solid. Explain the changes in the arrangement and movement of particles of argon as the temperature of the air decreased. So the first thing we have to consider is that as the argon cools down, the particles have less internal and kinetic energy. This means that the particles will change from being spread out to touching each other. They're going to collide more often, so we get the change of state of gas to liquid. The particles now are going to cool down further, which means they have even less internal and kinetic energy. The particles now change from being in random arrangements to having more fixed positions and only vibrating. This is due to the strong attractive forces between the particles, and so a change of state from liquid to solid occurs. A hybrid car has an electric motor and a petrol engine. Petrol is a non-renewable energy resource. What is meant by a non-renewable energy resource? So non-renewable means an energy resource that will run out. The electric motor in a car is powered by a battery. To charge the battery, the car is plugged into the main supply at 230 volts. The power used to charge the battery is 6.9 kilowatts. Calculate the current used to charge the battery. So here we're going to be looking at the equation power is current times voltage. So if we substitute our numbers in, now our power is 6.9 kilowatts, which means that is 6,900 watts, is going to be our current times our voltage, which is 230 volts. So rearranging the equation, the current is going to be 6,900 watts divided by 230 volts. And if we calculate that out, our current works out at being 30 amps. Mains electricity is an AC supply. Explain the difference between direct and alternating potential difference. So direct potential difference is where the current is always in the same direction, and alternating current, the current changes direction. The cable used to connect the car to the mains electric supply has a low resistance. Explain why it's better to use a cable with a low resistance than to use a cable with high resistance. So for the same potential difference, if we lower the resistance, that means that the current would be greater. So if we have a greater current, that means the car battery can charge faster. Figure 2 shows a circuit that a student built. The lamp has a resistance of 10 ohms. Each resistor has a resistance of 10 ohms. So what's the total resistance of the circuit? So the total resistance of the circuit is going to be less than 20 ohms, and this is because the lamp's resistance of 10 ohms is added on to the resistance of the resistance in parallel. Now, if each one of these in parallel is 10 ohms, then the total resistance in parallel has to be less than the lowest resistor in the parallel circuit. So if we add less than 10 to 10, it's going to be less than 20. Draw the circuit symbol for a thermistor in the box below. So the circuit symbol should look like this. The student increased the temperature of the thermistor. Explain how the current in the thermistor changed. So if you increase the temperature, the resistance decreases. And if the resistance decreases, the current increases. Figure 3 shows a circuit that a student built. Explain how the potential difference across the resistor and the lamp will change when the switch is closed. So, when the switch is closed, the resistor will have zero potential difference, and that's because there's a short circuit, an easier alternative route for the current to go through. Now, in terms of the lamp, the potential difference across the lamp will increase because now the current across the lamp has increased. A student investigates how the mass of water in an electric kettle affected the time taken for the water to reach boiling point. So when the kettle reaches the boiling point, the kettle switched off. The heating element of the kettle is connected to the main supply. Explain why the temperature of the heating element increased. So when connected to the main supply, the electrons in the heating element are going to collide with the particles that are there. This is going to increase the energy of the particles in the heating element. Give one variable that the students should have controlled. So one of the control variables would be the starting temperature of the water. Figure 5 shows how the mass of water in a kettle affects the time taken for the kettle to switch off. So we've got the time taken in seconds for the kettle to switch off and the mass of water in kilograms. Suggest why the line on figure 5 does not go through the origin, and this would be because the actual element is going to take some time to heat up in the first place. Suggest why the results give a non-linear pattern. So the pattern is non-linear because the energy transfer to the surroundings is going to change as the mass of the water changes. The power of the kettle is 2.6 kilowatts. The kettle took 120 seconds to heat 0.8 kilograms of water from 18 degrees Celsius to 100 degrees Celsius. Calculate the specific heat capacity of the water using this information and give your answer to two significant figures. So first of all, energy is going to be the power times time taken. So energy is going to be 2,600 watts times 120 seconds. And that gives us an energy of 312,000 joules. Now, using our second equation, energy is mass times specific heat capacity times the change in temperature. So this means that 312,000 joules of energy is the mass, which is 0.8 kilograms, times our specific heat capacity, which we're trying to work out, and then we have our change in temperature, which went from 18 degrees Celsius to 100 degrees Celsius, so that's 82 degrees Celsius. So if we rearrange our equation, we could work out specific heat capacity as being 312,000 joules divided by 0.8 times 82. And if we calculate that out, we get 4,756 joules per kilogram per degree Celsius. But if we give our answer to two significant figures, so we don't want to lose that last mark, that was going to be 4,800 joules per kilogram per degree Celsius. Lanthanum-140 is a radioactive isotope. A nucleus of lanthanum-140 emits gamma radiation. What happens to the mass and the charge of the nucleus when gamma radiation is emitted? So gamma radiation is not a particle, it's an electromagnetic wave. So the mass number stays the same and the charge stays the same. Why is it difficult to detect gamma radiation? Now, gamma radiation is very weakly ionising, which means most gamma radiation is going to pass through any kind of detector. Activity is the rate at which radioactive sources decay. A teacher measures the count rate from a sample of lanthanum-140 using a Geiger-Müller tube. Explain why the count rate was less than the activity of the sample of lanthanum-140. So when you get the radioactive source out, the radiation spreads out in all directions. The Geiger-Müller tube will only measure some of the radiation that passes through it. The teacher investigates how the thickness of lead affected the amount of gamma radiation that could pass through it. So we have a diagram of how this was done. Explain why the teacher stood as far away from the apparatus as possible. So because it's gamma radiation, the teacher wants to reduce the amount of radiation that they might receive because radiation can cause cancer or mutations. Table 1 shows results of an investigation where we have a source, we have some lead and we have a Geiger-Müller tube. So with different thicknesses of lead, the counts per second are measured with the Geiger-Müller tube. The teacher concluded that the count rate was not inversely proportional, and we've got to explain why the teacher was correct. So if we have a look at our first result at 0.5 centimetres thickness of lead, that gives us 110 counts per second. Now, if this was inversely proportional, if we doubled the thickness of the lead to 1 centimetres cubed, then the count rate per second should be half of what it was at 0.5, and that would be 55 counts per second. Now, if we look at our results, the actual counts per second is 60 counts per second, which is not 55 as it should be. So that means that it is not inversely proportional. Now, lanthanum 140 can also be emitted by beta radiation. So, complete the equation showing the decay of lanthanum 140 into cerium using beta radiation. So, beta radiation, electrons do not have a mass, but they have a charge of -1, which then means that our cerium would be 140 because our numbers have to add up when we're looking at our radiation, and then we've got 57 as our atomic number at the bottom there. So that means if we have -1 for our beta radiation, this must be 58. There are a number of isotopes of cerium which are radioactive. Different isotopes of cerium have different half-lives. The half-life of an isotope can be found by studying how the number of atoms change over time. So figure 7 shows how the number of atoms of cerium-148 in a 120 gram sample changes over time. So if we look here, if the number, we've got our number of atoms to start with, half of the number of atoms here would be 2.5 times 10 to the power of 23, because that's half of 5 times 10 to the power of 23. And if we take that across and take that down, we can see that the half-life is 50 seconds. Determine the ratio of the number of cerium atoms in the sample when it was 100 seconds old compared with when it was 350 seconds old. So, from the graph, we worked out that the half-life of the cerium is 50 seconds. Now, if we look at the difference between 100 seconds to 350 seconds, the difference is 250 seconds. And 250 seconds is 5 half-lives. So that is going to be a half times a half times a half times a half times a half, which works out at 1/32. So the ratio is 1 to 32. Determine the activity of the sample of the cerium when the sample was 20 seconds old. And we've got to use figure 7 to help us do this. So to determine the activity at 20 seconds, we need to work out the gradient at 20 seconds. So we are going to have to draw a tangent to start with. So it's going to be the number of atoms divided by the time. So having drawn our tangent and having looked at our number of atoms and change in time, we have 1.3 times 10 to the power of 23 divided by 26 seconds. So the activity is going to be 5.0 times 10 to the power of 21. So as shown by using our graph and the tangent, the number of atoms to get the gradient was 1.3 times 10 to the power of 23 divided by 26 seconds, which gave the activity as being 5.0 times 10 to the power of 21.